Okay, good day in class. Got a lot of problems done. Probably a lot of you are trying to get to number 10, and some of you even got to number 10. But I thought we'd take a look at that one with the young lady jumping on the trampoline, and she has we'll work this together. She has a downward velocity, so that means that if you take her mass times her velocity, you could have her initial momentum. That would be her initial momentum. That would be P initial. If you took her mass times the downward velocity that she has before she hits. Then they tell you that, I'm going to try to diagram this problem for you, that if you look at the force times the time, she had 3 successive impulses acting on her. So I'm just going to sort of make them look like rectangles. So she had an impulse that acted on her, time went on, and then another impulse, maybe it was bigger, maybe it was less, I don't care, and then maybe another one right here. And so if you think about the force times the time, well, F delta T, but only the delta T that we talk about, so that would be, I'll use a pretty red here, this right here, that delta T plus that delta T plus that delta T, and then times the force that was constant in all 3 cases, then F delta T equals M delta V. So what we need to do is determine the sum of these 3 impulses, because I told you that the area underneath here would represent the impulse acting on a body. And in this case, it's the young lady's body. And I think she came out okay with no hurts or bruises or anything. So we would end up getting the total impulse acting on her. So if you do that, I did it, and I think I got 340, I'm going to round it to 346. So I got the sum of the impulses, the sum of impulse, the 3 successive impulses, this is number 10, is equal to 346 Newton seconds. And so now we know this side of the equation. So I thought, well, how do I do, now what do I do? Well, they wanted to say, what is her final velocity? Well, I know that impulse equals m delta v. So if I then solve this equation up here for delta v, I would just divide both sides by m, and I would get f delta t over m equal delta v. So if I do that, I would get her change of the change in velocity that this impulse would cause. And then if I know her initial velocity, I can take the change in velocity away from it, and that would leave me with her final velocity. So, in other words, do you see what I'm talking about? I'm finding the change in velocity that she underwent when the trampoline pushed up on her to cause her to come to a rest. Well, I don't think she came to rest. I think there's a little bit of velocity left. So I think I ended up getting her change in velocity. You can put the numbers in. You're responsible for that, and you're responsible in general. 7.1 meters. I can't write per second. I gotta get a new stylus so I can be more styling. And so 7.1 meters per second. And then if you took away her initial velocity minus the change in velocity, you would end up with about, I forgot what, something. Yep. Okay. All right. So take a look at number 10 if you have an issue, and hopefully that'll help you see through it a little bit. All right? Okay, let's get to conservation of momentum. Conservation, part 2, right, of momentum. So this is just the conservation, your first conservation law. And the law of conservation of momentum simply states that in a closed, isolated system, so a closed, isolated system could easily just be those 2 carts that were on the track there, and that one's not touching the track, but it's close. Here, we'll bring the track up to it. Oh, that's not touching either. Okay, and so that's a closed, isolated system, even though it's out, but that's what they define as a closed, isolated system. So in a closed, isolated system, the momentum that you have initially is equal to the momentum final. So you could make a statement of P initial, anything that has momentum initially is equal to the P final. So that's the so what does this mean? That the initial momentum is equal to the final momentum in a closed system. So it means that you never lose any. So if you have a very simple case, we're going to use those carts again. So if I have this cart and it has velocity v, and it's going to strike and hit this cart with no velocity, so it's at rest. So we could say we're going to call this A and call this B again. And so we could say that the momentum initial, in this case, could be m times A times the velocity of A plus m times B times the velocity of B. So that's the initial setup, and it's going to hit, strike, and stick to. Remember, what type of collision would that be if it sticks to it? It would be a inelastic collision, and it will stick to. So when it sticks to, that means we combine the masses together. So we say, oh, well, then the momentum of A plus B together, so the mass of A plus the mass of B, and then they would have one common velocity, wouldn't they, since they're stuck together, times, and I'll put parentheses around that, times the velocity of A and B. So this is a statement, and the thing is, there's no set formula here or anything. It's just saying that the momentum initial, P initial, is going to equal the momentum final. And you could have three different objects. If it's a closed system, you could have four. I mean, it'd be silly to have that many, but you get the idea. Usually it's two or so, and all you did is you look at, well, what objects could have momentum initially. So could cart B be moving? Yes, it could. And in this particular case, it's not. So that's going to make it easier. So wait a minute. You guys are going to think that this is divided by. So I'm going to get rid of that. There's no divided by, right? So momentum initial equals momentum final. All right. So how does this all work out? Well, if mass of A equal mass of B, but B doesn't have any momentum initially, so let's see what we have here. We could say that the MAVA plus MBVB equal MA plus MB times velocity of A and B. So who didn't have momentum initial? We said B didn't. So if its velocity is 0, then if you multiply 0 times its mass, you get 0. So now we made the equation a little easier, and now that equals mass of A plus, but it does have mass, so we have to account for it over here, times the velocity of AB. And now if we wanted to get the final velocity of this system, then we could merely say, and I said that the mass of A equals the mass of B, so whatever the mass over here on this side will just be double what it is over on the left side. Do you see what I'm talking about? Because if mass of A equals mass of B, then we're going to have two. We could say that we could replace mass of A plus mass of A, so that'd be 2MA. Do you see what go back to the previous page and you'll see what I'm talking about. Since mass of A equals mass of B, okay, I'm wasting too much time on that. All right, so times VAB equal mass of A times the velocity of A. And then if we divide both sides by 2 times the mass of A, we end up getting mass of A times the velocity of A over 2 times the mass of A. And then look what cancels out, mass of A. So the velocity of AB would be velocity that A had divided by 2, or half as much. And see if that makes sense. So let's just, if you think about what you had before, you had mass of A times velocity of A. And then over here on the right-hand side of the equation, you double the mass. So if you double the mass, what did you have to do to the velocity in order to get it to stay equal to the mass of A times the velocity of A? You had to decrease the velocity by 2 times, or 1/2. So that's a simple conservation of momentum. And let's see, it's pretty neat. You can talk about that momentum is conserved in all kinds of, it's always conserved. So momentum is always conserved. And what do I mean by that? I mean that in a closed, isolated system, momentum before always equals the momentum after. Where does it go? If two cars hit and they collide, they had momentum before, where did it go? Well, you can start getting tricky about it, and you can talk about, well, it went into heating up. Like, for instance, there was a lot of heat generated from a car sliding to a stop, and that heat, this is going to get very small, that heat went into heating up the air molecules in the air around the immediate vicinity, and those air molecules gained a greater velocity. Now, air molecules have mass, and so they actually moved faster at that point, so they took the momentum there. In general, that's where it's lost to. And remember, I said as long as it's a closed, isolated system, so two cars crashing or something like that, where they're colliding, then they don't. You don't necessarily have your momentum is conserved, but it's changed into some other or given to other products like small molecules, for instance. So, couple more cases about momentum. If you had the cart and it's going along and it hits another cart, like here, but so here it is with V in this direction, and let's say that this cart is very massive. Let's put another little bitty mass on top, almost like a cake. It's a cake cart, and so this cart is much less massive. A is much sorry, got to do it the right way. A is much less. Much less than B, and so it could literally strike B, and then rebound backwards. So in the after scenario, you could have B going this way, and A could actually that looks pretty bad, be going back this way. But still, because it's vector quantity, the momentum of B, the momentum that B has going in this rightward direction, minus the momentum that A has going back in the opposite direction, would still equal only the momentum that the cart A had before the collision. Now, I'm assuming cart B was at rest beforehand. So what I'm trying to say is that you have to account for the vector nature of momentum. The vector nature. And that means that you have to pay attention to sign. And wrapping up, I just wanted to briefly mention that concept of F delta T again equal M delta V. When we looked at that, we still getting a little confused on this. All I'm trying to say on here is that if you have a force and it acts over a given amount of time on an object, it will cause a change in that object's momentum. In other words, for our class, it will actually cause a change in the velocity of the object. And so if you change the velocity, then you obviously had a force acting on it back from Newton's second law, F equal ma, because if you change the velocity, then you were accelerating the object. So you had to have a force acting on it. So the idea of impulse, Newton seconds, is just that concept. It's just saying, oh, if I have a force and it acts over a period of time, that is going to cause a change in momentum of that particular object. Notice that P equal mv and F delta T equal m delta v deal with only single objects, whereas the law of conservation of momentum deals with multiple objects hitting and striking and colliding with each other. All right, well, we'll stop right there, and I'll get this uploaded, and hopefully you can watch it tonight. All right, bye.